So in this chapter, we will look at dynamic analysis of induction machines in terms of DQ windings, and then this will allow us kind of seamlessly to do vector control that we'll uh, see later on. So as a brief background, in the previous chapter, we saw that in a machine, induction machine, if you replace the squirrel cage by three equivalent rotor windings, then we have six windings, and they are mutually coupled. And we saw the flux linkage and in the stator and the rotor, and then we also wrote the voltage equations, and we realized that they can of course be solved in spite of this dependence on the rotor position theta sub m, but they do not give us a clear picture as how to control them. So that's really the objective of this chapter here. So here what we'll do is we will represent the stator MMF, and the same thing we'll do for rotor MMF, by equivalent DQ windings. We realize that in reality we have three phase windings, A, B, and C, and together they are producing a resultant MMF. But that MMF can be also produced by an orthogonal set of DQ windings, as shown here. One on D axis, and the other one, we call it Q axis. So there are two windings here, and they are orthogonal to each other. And this angle theta sub dA, the angle of D axis with respect to A axis, theta dA, let's say, is arbitrarily chosen. It could be anything. Okay, but in selecting these DQ windings, we'll make sure that first of all, each one of them is sinusoidally distributed in space. We'll assume that these are hypothetical windings; they don't exist, and the number of turns they have is equal to square root of 3 over 2 times the number of turns per phase of any of the ABC windings. And the reason we choose this ugly factor of 3 over 2 is because we want the magnetizing inductance of any of these D or Q windings to be the same as the per phase inductance that we saw in ABC frame. And so in ABC, when we're talking about the magnetizing inductance of phase A, there was contribution to the flux linkage in phase A from phases B and C. That doesn't exist here. Okay, so because the D and Q windings are orthogonal to each other by design, and therefore they don't interact with each other, in terms of contributing flux linkage, and therefore this number of turns have to be larger by a factor of square root of 3 over 2, so that when you square it, because the inductance is proportional to number of turns squared, so when you square this factor of square root of 3 over 2, it becomes 3 half, and we saw this factor of 3 half coming in the expression for the magnetizing inductance L sub m as opposed to the magnetizing inductance of single phase, LM single phase. So that's the reason we choose this factor of square root of 3 over 2. Okay, so now the space vector that we get for the stator current is the definition we have seen earlier, and the MMF that this produces, stator MMF produced, and again represented with respect to A axis. We can show that in terms of the current space vector like this times the number of turns per phase divided by 2. And so this and these three currents flowing in respective A, B, and C phases are producing this stator current space vector I sub s. But now we would like to get the same MMF that this space current space vector is producing by ISD and ISQ. So that's what we are doing here. We are saying that these currents are flowing through applying the same expression here, that the number of turns for these windings happens to be square root of 3 over 2 ns, and then this factor of 2 is here, and the current that we have is ISD plus JISQ, and this quantity in brackets is IS with space vector defined with d-axis over here. So ISD plus JISQ is this uh, current space vector were defined with respect to d as the reference axis. And so from here we can simplify and say that ISD plus JISQ is equal to square root of 2 over 3 times this current space vector, defined with respect to d-axis. So the bottom line is that the actual value of ISD and ISQ that we have to have in order to produce the same MMF that these three ABC windings were producing, it depends upon this angle theta sub dA. Whatever this angle you choose, well, that makes a difference. As you can see here, that you take this IS space vector, which is the same as here when you have three-phase windings, let's say, and you take its projection onto the d-axis and you multiply that projection by this factor of square root 2 over 3, and you get ISD. And the same thing you do for q-axis by looking at the projection on the q-axis. So obviously how large that projection is depends upon the angle theta dA value, okay, at any given time t, for example. So we'll go with this, and we'll do the same thing in the rotor circuit. There's hardly any difference. In this case, we have at any given time t, let's say the rotor current space vector is over here, and then we have these windings along D and Q axis. Here I should emphasize that this set of D and Q axis that we choose, they have to be the same for the rotor as for the stator. Otherwise, all the advantages are gone. Okay, so they are the same in both cases. So now you can see that, and again, the number of turns on each of these rotor D and Q windings would be equal to square root of 3 over 2 times n sub s, right? And so again, we take the projection of IR space vector onto d-axis and multiply it by this factor 2 over 3 square root to get IRD, and the same thing we do for IRQ over here. So that's a very similar, identical process. Okay. So now we come to the case where both currents are present simultaneously. What good is this machine if only one set is present and another one is absent? So we have both IS and IR, and they are shown in totally arbitrary position, because just for definition purposes, because in reality they will be very different in different positions with respect to each other at any given time. So this is totally arbitrary, as I said. So let's take IS here, and you can see that we can calculate ISD as before and ISQ as before, and then similarly we can, for given IR, we can calculate IRD and IRQ as we have done before, right? So having done this, what we see is that we can write the flux linkage of these windings just by intuitively. It can be done mathematically. It might take 1 or 2 pages, but here we can just look at intuitively and just concentrate only on one expression here. Everything else is very similar. So this is the expression for flux linkage in the stator D winding. Okay. So first of all, the flux linkage in this has no contribution from Q axis, either the stator or the rotor, because Q axis, Q winding is orthogonal to D axis. Okay, and so that's one thing. The second thing we see is that the first term is due to the current in the stator D winding itself. So here this L sub S is the the leakage plus L sub m. So that's the self-inductance of the stator D winding here, right? So that is something which is then taking care of not only the magnetizing flux, and that's where L sub m comes in, and also the leakage flux associated with the D winding, and that's where the leakage inductance comes in. Okay, and then we have another term which is due to the magnetic coupling between the rotor and the stator. So by having current in the rotor D winding, we have this term L sub m times IRD that is contributing to the stator flux linkage in the D axis. Okay, and we can make the same argument for these other three expressions. No difference. Okay, is the same argument. So here, let me just point out the different angles that we have. One of them is theta dA we talked about. That's the angle of D axis with respect to stator A axis, which is stationary. And then we have theta sub m, which is the rotor A axis. So as rotor rotates, of course, this angle theta sub m is changing, and then at a given time we can see what the whatever this D axis happens to be, we can measure it with respect to the rotor, I shouldn't say measure, but we define it with respect to rotor A axis over here. So that's theta D uppercase A. So these are the different angles that we have, and this is at any given time, and these vectors, space vectors, will be rotating in time, and their relative position may be very different than what you see here. Okay, so now what we described was very kind of I would say to give us a very good visualization, but using these hypothetical D and Q axis windings, which can rotate in stator and the rotor. How can windings in stator rotate? Only if they are hypothetical, right? So in this case, they do, and but we can make it more mathematical, because that's what we will need in order to be able to simulate this machine in terms of this DQ windings here. So we see that if these are the three phase currents we have at any given time, IA, IB, and IC, and by using this transformation matrix, which is dependent upon this angle theta dA, we can calculate ISD and ISQ. Okay, at this time, and the same thing we can do for the rotor D and Q windings, given the rotor currents I, capital A, capital B, and capital C, but this time the angle we have is not theta dA, not this theta dA. Rather, in the rotor case, it's theta D D axis with respect to rotor A axis here. So that's something we have to keep in mind. Otherwise, the two matrices are the same. Okay. So now we know that in the stator, these three currents add up to 0 because of the Y connection and Kirchhoff's current law, and similarly in the rotor, these three currents add up to 0. So knowing this, we can then compute sort of a reverse transformation going from ISD and ISQ to ABC here for the stator as well as for the rotor over here. And again, this angle theta dA here and theta dA over here. So those are the two angles that we have to use here. Okay. So now we have these equations for transforming voltages and currents, and we have defined flux linkages in terms of these currents, as we saw early on. So we should be able to write the voltage equation in D and Q windings. So this requires a little bit of care here, that first of all, in ABC frame, we can write this expression, because if you look at any phase voltage V sub A, what is that? RA times IA plus d lambda A dt, right? So you can write these equations for all three phases, and we can put it in this matrix or vector form or whatever you want to call it, right? So now we will multiply both sides of this equation by this transformation matrix. We want to go from ABC to DQ. So we multiply it by this transformation matrix, which is this one here, on the top over here, on the left side, and we do it on the right side. R sub s we can pull out uh, early on because that's just a constant, right? And then we multiply the same transformation matrix on this term d dt lambda q abc, this term over here. All right. So here, um, certainly when you apply this transformation on ABC, it leads to dq over here for the voltage. And similarly, when you apply this transformation on IABC, it leads to IDQ over here. But now this term here requires a little more care. First of all, we write it down. This transformation matrix is here, but this lambda ABC can be written as the lambda dq times going from dq to abc. So you can see that this combination, the product of these two, is the same, which we are taking a derivative of as lambda abc here. Okay, so just writing lambda abc in terms of lambda dq and the transformation matrix that is involved and that we have seen earlier, right? So once again, if we try to simplify this, that this voltage in dq is equal to Rs times I in dq. And so here what we will do for this second term on the right hand side, we will do differentiation by parts. Okay, so first what we will do is we will pull out this term over here outside, as you can see here, and then we will apply, no, I'm sorry, let me back up here. So first what we'll do is we are trying to differentiate. Let me see if I can erase all these things over here. I think I can. Erase all ink. Okay, so all the ink is gone. Okay, I'm sorry, I have to back up here and explain again. So this is the term we're talking about, and here this is the time derivative of two terms which are both time dependent, because even this transformation matrix involves theta dA, and that theta dA is dependent upon time as the d-axis is moving, and so also this flux linkage here. So we have to differentiate by part. So let's see, what do we do here? Well, first of all, we have this coefficient here, which is right here. Okay, and then we just differentiate lambda dq right here. Therefore, this part here shows up over here, like this here. And once again, if I could, I would erase all ink here. And so the third term in this right-hand side that shows up, first of all, this matrix shows up here. No surprise there. But this time, when we do the differentiation, we are doing it on this part over here, Ts from dq to abc, and lambda dq is over here. Okay, so when you multiply these two matrices, we get a unity matrix over here in this term. And in this case, we have time differentiation of this transformation matrix, and that is involves differentiating theta dA with time, and that we call the speed of d-axis with respect to stationary a-axis. we could have called it theta d little a, but who wants to carry this a over here? So we'll not use that. And so the product of these two terms would give us this matrix here. So it's just a simple algebra, but that we'll not go through, but you can do it on your own. It's pretty straightforward. So we have this voltage equation in dq. Okay. So I have written it down again, what we saw early on. And so if you take the real part and you take the imaginary part, we get two equations. One of them is this, and the other one is this. So let's just look at the form of this equation. VSD, the voltage in the stator D winding, of course, has this voltage drop due to ISD across its resistance. Then it has this term, time derivative term of lambda SD, the flux that is linking it, but it also has coupling from Q axis, and that is by this term, third term here. It's called speed term here, minus omega d, which is the speed of d axis with respect to stationary A axis, times the flux in the stator Q winding. Okay, so that is something to remember. And then when it comes to VSQ, again we have this voltage drop, we have ddt term, and this time it's plus omega d plus lambda st over here. Okay, and the same thing we can do for the rotor. There's no difference, and the only thing to remember here is that in this case we are talking about the rotation of d axis with respect to the rotor A axis here. Okay, and maybe I should have drawn it with a slightly different angle because the stator, okay, let me rewrite it here. So let's say stator A axis is over here, A axis. Rotor axis A is over here. And then the D axis is over here, right? So this angle is theta DA, okay? So in the rotor, we have this angle, and then it's really the differentiation of time differentiation of this angle that gives us this omega dA. And that turns out to be the slip speed, okay? And whereas omega d may turn out to be the synchronous speed, depending upon the choice of the D and Q axis, how they are rotating. So the bottom line, oh, I'm sorry. The bottom line is that these equations can be written in this this form here, vector form for VSD and VSQ, and ISD and ISQ, and the derivative of time flux linkages, and also how these flux linkages lead to the speed term over here can be written in this form, and that has the same role as J in this equation over here. So let's not worry about it because this is the equation we are going to use. Okay. So and as we saw early on, we can do the same thing in rotor, and we have if you separate the real and imaginary terms, we have these two equations here where theta, the time derivative of theta dA is omega dA over here. So that is the instantaneous speed of winding set in air gap with respect to rotor A axis. I'm not sure what this term here is, but anyway, and this omega dA is equal to omega d minus omega m, and you can see that very clearly here. This is A axis here, this is rotor A axis, this is D axis over here, and this angle here is theta dm. Okay, this angle here is theta dA, and this angle here is, I'm sorry, not this angle, but this angle here is theta dA. So as you can see here, that theta dA is equal to theta d lowercase a minus theta sub m. So if you differentiate this equation, you'll get omega, the speed of d axis with respect to rotor A axis equal to differentiation of this, which is omega d, and differentiation of this, which is omega m here. Okay, and it's important to note is that in two-pole machine, it doesn't matter, but if you have more than two poles, then this omega m that we are talking about here is in electrical angles. Well, it's electrical angles per second, so it's really the mechanical speed of the rotor uh, in mechanical radians per second times the pole pair p. No, number of poles. P is not pole pair, it's number of poles, right? So therefore, when P is equal to 2 for a two-pole machine, the electrical speed and the mechanical speed are the same. Okay. All right. So uh, whatever we did for the stator, we can do for the rotor. So we have a very similar expression over here, and this we can use to obtain fluxes and current with voltages as inputs. Okay, so we can rewrite those equations that you saw here. We pull out this term on the left hand side, ddt of these flux linkages over here, that they are equal to the voltages that you're applying here and the drop across the resistance, and then the speed term over here. So it's just a matter of rewriting those equations we have seen earlier. No surprise here. And then uh, we can uh, perhaps define this term lambda s dq, which includes both an d and q axis, and similarly vs dq, and with that, and lambda s dq and lambda r dq, and as we have done, and we can write these equations here, and then if you are using Simulink, for example, you may be using some other simulation program, or you may be writing it and solving it and using some kind of engine like MATLAB, but we find here much easier to use Simulink based approach. And here you can see that you can draw a block diagram where these are the voltage inputs here. In a squirrel cage machine, this will be equal to 0, okay, VR dq, and then the speed of the d-axis and the speed of the rotor a-axis. Speed of the d-axis with respect to rotor a-axis shows up over here, and then you can just make use of these equations to draw these block diagrams and use the resistance drop here, like here, coming from the currents IS dq and IR dq, and you sum them up to get these derivatives terms from these two equations over here, and then you integrate that and you get the flux linkage. Because when you integrate this, you get lambda r dq over here. When you integrate this here, you get lambda s dq. And then we can take these flux linkages and then have a transformation matrix that give you these currents, I dq, which is IS combination of IS dq and IR dq. This is something which we haven't covered. So this part we haven't covered yet, and we'll see it in our next module. So thank you very much. So here, David, we have to discard